Hi, good morning, everyone. Are there any questions before I start? All right, if not, then let's continue today's lecture. Start today's lecture. Last time we talked about formulas and how to define a well-formed formula and how to construct and how to check whether a given string of symbols in our alphabet is a well-formed formula or not. Today we are going to introduce some new concepts, and before that we want to start with this convention. We're going to introduce the priorities for our connectives so that if we don't write brackets, we understand what the formula is. So as you saw, we put a lot of brackets around the formulas. Some of them are necessary, some of them are not necessary, and they could be dropped if we have some sort of agreement placed. So first of all, outermost brackets are redundant. So if you have a formula, bunch of symbols, and the outermost ones, they're not doing anything, you could drop them. So if you have a formula of the form P and Q, we already had the brackets on them. Officially, there are brackets. So now we say that we could not write brackets. And that again does not mean the brackets are not there. We're just not writing them. So they are invisible. And the priorities of connectives decreasing from left to right are: the highest priority is with the negation, then conjunction, and then disjunction. Conditional and biconditional has the least priority. And also, if we have a formula of this form, there's formula A, and there's conjunction from left and right, and there's something here like B and C here. Now, how do we understand this? We understand this that the one on the right has higher priority, so this one applies first. Actually, in the terms of semantics, it's not going to make a difference because these formulas are going to be tautologically equivalent. But syntactically, we agree that since conjunction is repeated twice, so there's no priority over any other connective, but we give the higher priority to the one on the right. So the right one applies first. So for example, that means negation of P. If I write negation of P, I mean this, there are brackets. If we write P or Q or R with no brackets, this is the formula, since this is OR here, and OR is the same connective. The one on the right has the higher priority. So it's this and then also outermost brackets. So this is short for this. Now, how about this one? Again, the one on the right has the higher priority. How about this last one? Well, now we know that conjunction has higher priority than disjunction. Therefore, this one is going to apply first. Then now between these two, connected this and this. Now, which one applies first? The one on the right. So this one applies first. And then finally, the last connective that applies here is this OR in the middle. So let me give you another example. I'm just going to write a formula. Negation of P implies Q, or negation of R is equivalent to P and Q. So I just wrote a random formula without any brackets. So let's see, what is this formula according to our agreement now? So, sorry, let me leave a little bit more space so I can place the brackets already here. All right. Here I have OR here and here. They have higher priorities over the other two connectives. So I know that this end applies here before this connective by conditional, because conjunction has higher priority. Negation always applies. So this is not the negation of this whole thing, but it's the negation of R, because negation has higher priority. So it's the negation of R, right? Now, between this and this and this, OR has the highest priority, so OR applies next. And now between these two, by the way, there's also a negation here. So it's the negation of P, not the negation of P and the rest of the formula. So negation only applies to P. So now if I wanted to put all the brackets, then this is also there's a bracket here as well. And then finally, there's this last bracket. Note that implication has higher priority than by implication. So when you place all the brackets, this is the actual formula. But as you can see, there are a lot of brackets. Sometimes you don't want to write these many brackets. So that's why we have this agreement and this convention that if we didn't write all the brackets, then we understand. Certainly not writing the outer ones is a good idea, because it doesn't hurt and it's quite obvious what implies what, or in this case, what is equivalent to what. But just to be precise, there are brackets here too. Any questions? All right. Now we're going to continue with the very important notion, that is induction. You should be familiar with the induction method in mathematics in general. I'm going to assume that you know what induction is. The usual induction, the first induction that you learn is induction on natural numbers. But then you also learn that anything that is recursively defined could be, we could use induction to prove statements about any recursively defined object. And here we define formulas recursively, right? Anything that is recursively defined, you could attach a notion of complexity to it, right? When you define something recursively, first you define the basis step. Anything that is defined in the basis step is going to have complexity 0. And now the complexity of a general object that you have defined recursively is how many times you apply the recursive step. So the number of the times that you apply the recursive step is usually called the complexity of the object that is recursively defined. In this case, what does it mean? We define the formulas recursively. We said that those atomic formulas, namely the variables and constants, they're the basic formulas, right? Those are those were defined in the basis step, so they're going to have complexity 0. So the complexity of the formula is in the atomic formulas is 0, and then how many times you apply the recursive step, that corresponds to how many connectives you have: negation, disjunction, conjunction, and or by implication, implication, right? So this is why we define the complexity of the formula to be the number of its connectives. That is, by the way, when I say connectives, I'm including negation as a connective. That is how many negations, conjunctions, disjunctions, implication, and by implication symbols are in the formula. So for example, if you see a formula like this, by the way, this is a formula, there are no brackets, but we understand this, that this is the negation of P. It is equivalent to Q implies T, and then finally this, right? Based on the priorities of brackets. But in any case, what's the complexity of this formula? 1, 2, 3 connectives. So the complexity is 3. What's the complexity of P alone? 0. What's the complexity of top? 0. These are atomic formulas, right? What's the complexity of negation of P? 1. Exactly. What's the complexity of negation of P? And T and top is 2, right? So this is exactly how we define complexity. Now we have a longer formula here. What's this complexity? 1, 2, 3, 4, 5. This actually, as I said, corresponds to how many times we apply the recursive step of the definition of formula to define this formula. So here's an easy proposition that follows from our definition of complexity. A formula has complexity 0 if and only if it's an atomic formula. Any non-atomic formula would have complexity greater than 0. Now, the complexity is usually used in an induction method. Again, any object that is recursively defined has complexity. It could have complexity defined in a similar way. And then induction is a very powerful method to prove statements about the recursively defined objects. So this is something that you learned as a structural or induction in your MATH1090 course. So suppose P of A is a statement about the formula A. Right? It says something about formula A, like formula A has Well, here I have an example that has like equal number of left and right brackets. Right now, you want to prove this statement about all well-formed formulas. You want to prove that all well-formed formulas have this property P. Then you can use induction. How does it work? First, you show that the objects of complexity 0 have this property. That is, you show that all the atomic formulas have this property P. That is, P of A holds for all the atomic formulas A. So that means, again, show that P of A is true for all the variables and constants. Now, in the inductive step, that's the basis step. Now, inductive step, you first take an hypothesis called the inductive hypothesis. You assume that this property P is true for all the formulas A of complexity less than a certain number A. N or K, doesn't matter. So you assume P of A holds for every formula A of complexity less than N. This would be your inductive hypothesis. And now you prove that every formula of complexity N has this property P. That is, P of A holds for every formula A of complexity N. So this is strong induction, right? You could, if you just assume this is true, P of A is true for all the formulas of complexity K, and show that it's also true for all the formulas of complexity K plus 1. That's the usual induction. And now this is the strong induction, but they're equivalent. That's also something that you've learned in your discrete math course. All right, but what does that mean? Let me restate the induction principle tailored for our use. This form of induction is called induction on the complexity of the formula, right? So how does it work? Again, suppose you want to show that P of A is true for every formula A. First, basis step, you show that it's true for all the formulas of complexity 0. That is, show that P of A is true for all the constants and variables. Now, in the inductive step, you assume that this statement is equivalent to the previous one that I said. You assume P of A and P of B, they both hold for formulas A and B. And now you show that P of negation of A is true, P of A and B is true, P of A or B is true, P of A implies B is true, and P of A is equivalent to B is true. This is equivalent to the previous one. This is equivalent to showing that you assume any formula of complexity less than certain number N has the property, and then you prove that any formula of complexity N has the property. This is equivalent because when you assume these, you're assuming that the property is true for all the formulas of complexity less than complexity of A and B. So you take the maximum of the complexity of A and B. If it's like the maximum is 7, then you assume it's true for any number of complexity less than 7, but you don't take actually 7, right? You fix a constant number, right? K or N. And P of A and B, P of negation of A, and all of these formulas here, they have complexity higher than those numbers. or that number, the maximum of the complexity of A and B. So this is equivalent to the general principle of mathematical induction that I mentioned. So it's more convenient to apply this, and eventually it boils down to this one. This is what you should check. So here is an example of how to apply the induction on complexity of formulas to prove a statement about all formulas. Prove that every formula has the same number of right and left brackets. This is kind of obvious. The way that we defined the notion of formulas, we always put symmetric brackets, right? If you wrote a left bracket, we also closed it with a right bracket, and so on. But how do you prove this? Well, the only way to prove this is by induction. Note that you want to show that this is true for all formulas. So you show that this is true for all the complexities. By the way, this is a meta theorem. Anything that uses induction is going to be a meta theorem. We haven't proved any theorem within our system yet, but that would come when after we introduce the axioms and rules of inference, and theorems that we prove within the system, they are going to be called theorems. This word meta refers to statements that we prove about our logic, not within our logic. So how do we prove this? First, show that the atomic formulas, every atomic formula has this property, meaning every atomic formula has the equal number of left and right brackets. Well, atomic formulas have no brackets. Actually true. Why? Atomic formulas are P, top, bottom. There are infinitely many of them, P, Q, and so on, right? There are infinitely many variables and two constants, top and bottom. None of them have any brackets. That means the number of the left brackets is 0. The number of right brackets is 0. 0 is equal to 0. Therefore, the statement holds. Now, the inductive step, assume that, so here we are going to first take our inductive hypothesis. We assume that A has n right brackets, and the statement holds for A, meaning A also has n left brackets. So we assume the statement holds for A and B. What does it mean it holds for A and B? Meaning A has equal number of left and right brackets. Same for B. B has the equal number of right and left brackets. So now we want to show that the statement is true for negation of A and B, A or B, A implies B, A is equivalent to B. So in order to do that, let's count the number of brackets in each of these formulas. But it is more convenient if I gave numbers. So assume A has, by the way, this is our inductive hypothesis. Assume the number of the left brackets of A are n, is n. And that means the number of the right brackets is also n. And for B, call that number to be m. B has m right brackets and m left brackets. And now, how many brackets does negation of A have? How many left brackets? A has n left brackets. There is one extra. Sorry, left brackets. There's one extra. So it's n plus 1. So negation of A has n plus 1 left brackets. How many right brackets does it have? A has n right brackets. There is one more here. This one, this right bracket. So it has n plus 1 right brackets. Now, how about this one? A and B. How many left brackets does it have? A has, note that we have used the notation A for a string of formulas, right? Sorry, string of symbols. And that string has, by our assumption, n left brackets. B also has m left brackets. So there are n left, let me write this like this here. So we have A and B, but this is in fact statement A here. This is our A, and then we have and this is our B, and then we have this. A has n left brackets. B has m left brackets. Now A and B has n plus m plus 1 left bracket. And the same is true for the right brackets. Has, by our assumption, inductive hypothesis, A has n right brackets. B also has m right brackets. And there is one more right bracket here. So A and B, this formula has n plus m plus 1 left brackets and n plus m plus 1 right brackets. So the number of the left and right brackets are equal. So it's a statement that was sort of obvious, but this basically showcases how you prove statements about formulas using induction and the complexity of formulas. Any questions here? So it's the general method that is important, and it's always similar to this. Steps are similar. All right, so we're going to do more inductions later on. So let's introduce our next notion. It's the notion of immediate predecessor. Constants and variables do not have any immediate predecessors. Immediate predecessor refers to the formula that is constructed right in the step right before constructing your formula A. If you have constants or variables, so variables like P or Q, and a constant like top or bottom, they don't have any, they're not constructed from anything, right? They are atomic. They do not have predecessors in terms of the sub-formulas. So we define, this is the definition, right? The immediate predecessors of the atomic formulas to be empty. They don't have immediate predecessors. Now, for any formula A, the immediate predecessor of negation of A is A. Because negation of A is constructed in one step from A. You just apply the negation. So it's the immediate formula that is sort of predecessor of negation of A. So the immediate predecessor of negation of A is A for any formula A. Now, for formulas A and B, A or B, A implies B, A is equivalent to B, the immediate predecessors are A and B. So they have two immediate predecessors, A and B. So this is again a recursive definition. Oh, it's actually, no, it's not exactly a recursive definition. Yeah, this is a normal definition. So for example, I have this formula here. What are the immediate predecessors of this formula? This formula is constructed by taking the equivalence of these two formulas. That is, this biconditional connective is the last one that applied. That means if I call this A and this B, then we are talking about the formula A is equivalent to B. And the last step in the construction of this formula was taking this equivalence. That means the immediate predecessors of this formula are A and B. So immediate predecessor refers to the last step, the formulas that are used in the last step to construct your formula. Atomic ones, they don't have any. They're not constructed from anything. Negation of A is constructed from A. So there's only one immediate predecessor. But the other formulas, when you have, for example, A and B, is constructed in the last step by taking the conjunction between A and B. So it has two immediate predecessors. Now, the reason that we define this, because yes. But yes, the connective with the least priority. Well, actually, when there are brackets here, it doesn't even matter if whatever I wrote here, if I wrote and here, it's the same, right? Because there are brackets. The immediate predecessors would be these two. All right, there's this formula that's, again, it looks pretty obvious. It says that for any formula, the set of its immediate predecessors is uniquely defined. What does it mean? It means that for any formula you take, like this one, no matter how you construct this, and there are different ways of constructing this, at least for if you want it to be like a computer. When I say different ways, for example, you can first take P or Q, this disjunction between P or Q, or no, you can first take negation of P and then take the disjunction with R and then take P or Q, right? It's just which operation you do first. It could be slightly different. So there are different, in terms of the order of the operations, there are different ways to construct a single formula, but that does not change what the immediate predecessors of the formula are. Always the last operation that you do is going to be for the same two formulas. And this basically tells you that essentially formulas are constructed uniquely, modulo that the freedom in the order that we have. So this is called the unique readability. It's proved by induction on complexity of the formula. It's in your text, but I'm not going to prove it. You could look at it. I'm also not going to ask you to prove it. It's a good exercise to learn how to do induction. So you could take a look at it. But the reason that we stated this theorem is that the unique readability implies that there's a unique way of constructing each formula from its variables. Again, when I said unique way, modulo that order between the when we have equal priorities and you have you start that order that I just described here, for example, the modulo that the construction is unique. And that, for example, implies that, for example, if I have a formula like this, let me write another formula. Again, a random one. P implies negation of Q is equivalent to negation of P or top. Yep, I guess. Yeah, this formula. I didn't write the brackets, but we understand where the brackets are, right? The brackets are here. Negation of P also has bracket here. Okay, we don't have to write that one. It's the negation of P or T, and the negation of Q. P implies negation of Q. Brackets are here. Now, how is this formula exactly constructed? I can exactly say how they're constructed by writing its immediate predecessors. This one has two immediate predecessors because it's a formula A equivalent to B. So immediate predecessors are P implies negation of Q and negation of P or top. Now, what are the immediate predecessors of this formula? If I continue this way, now this one it's the formula of the form A implies B. So immediate predecessors are P and negation of Q. Right? What are the immediate predecessors of this? Negation of P and top. Now this one has one immediate predecessor, that's Q. This one's immediate predecessor is P. And now we're ended up with all atomic formulas in the bottom. So bottom of each branch is an atomic formula. So this is a unique tree. In terms of a tree, this is a unique one. This means this formula is constructed by taking a negation of Q and taking a negation of P. Again, order of this doesn't matter. You could take the negation of P first and take the negation of Q first. This order doesn't matter, but you first take the negation of these two and then take the implication. P implies negation of Q in the next step to get this. Take the disjunction of negation of P and T, you get negation of P or T. And then you apply the last connector. Yes. Can you just go through one more time what you mean by it? It's a unique thing. Okay, I don't want to go through the isomorphism of trees. That goes back to graph theory. So then I say unique tree. It's actually, if you knew as two graphs, two trees, these are going to be isomorphic. But I don't want to go through it. It's not important for our case. So just you can trust me that at least the shape of the tree is the same. no matter how you write it, there's no other way of writing this. When you write the immediate predecessors, obviously I could write, for example, T here, negation of P here. That doesn't change anything. This kind of order doesn't matter. But in terms of isomorphisms of trees that you learn in graph theory, this also is an isomorphic tree to the other one. Yep. Well, unique again, as I said, is if I wanted to be very precise, unique modulo the isomorphisms of trees like this, right? Isomorphic trees are the same. So modulo the isomorphism is unique. But when I said here, the unique readability theorem, it says the set of immediate predecessors are unique. That's what I meant. In terms of uniqueness, it would give you always the same immediate predecessors. And you take the immediate predecessor of your formula, it's a unique set of formulas. Take the immediate predecessors of those sub-formulas, again, it's a unique set of formulas. And this is what I meant by being unique. All right. Now, let's go to inductive or recursive definitions. This is also a general thing that if you define an object recursively, then you can define concepts for that object recursively. It's called a recursive definition or inductive definition. There are many ways. I'm pretty sure you have seen the definitions, recursive definitions of sets and objects previously in your, I think, discrete math, at least, discrete math courses. But how does it work? First, you define a concept for all atomic formulas. Then define a concept for negation of A, assuming that you have defined the concept for A. So you use the definition of the concept for A to define the concept for negation of A. And now you assume you've defined the concept for both A and B. Then you give the definition of the concept for negation for A and B, A or B, A implies B, A is equivalent to B. Now, there are a lot of examples of definitions of concepts of different concepts on formulas using recursion. We're going to see a lot of those in the following weeks, but let me give you an exercise. So exercise or example, define the complexity of a formula, or the notion of complexity using, or sorry, recursively. Previously, I defined the complexity. How did we define it? We said the complexity of the formula is its number of connectives. That's an okay definition, but a better definition, a definition that would actually work for a computer, for example, would be a recursive definition. How do I define the notion of complexity recursively? I first define it for those formulas of complexity 0. That means atomic formulas. So that would be this step. How do we define it? We say every atomic formula has complexity 0. Now, you assume you know the complexity of A. The complexity of A is defined. You define the complexity of negation of A. What's the complexity of negation of A? It's complexity of A plus 1. Right? So this is how you define the next step. So the complexity of negation of A is complexity of A plus 1. Now define the concept of now we want to define the complexity of A and B, A or B, A implies B, A is equivalent to B, assuming that we have defined the complexities of A and B. How do we do that? So suppose the complexity of A is N, complexity of B is M. What is the complexity of A and B? Anyone? Yes. Exactly. N plus M plus 1. That's how you define this. What's the complexity of A or B? The same. N plus M plus 1. And same for A implies B, and A is equivalent to B. So this would be a recursive definition. And it's a much better definition. All right, we're going to define more concepts recursively instead of formulas later on. But let's move on from semantics. So far, we talked about only semantics, how to construct formulas. It was completely syntactical. We haven't talked about semantics at all, right? Semantics concerns with whether a proposition is true or false. So let's talk about the semantics of formulas in propositional logic. Again, this is something that you've learned before, so I'm going to move on quickly here. Any formula, we previously called those propositions. Formulas are propositions here, meaning they are either true or false. Has a truth value set of true or false in propositional logic. The value of top, this constant symbol top, is always going to be true. And the truth value of bottom is always going to be false. The truth value of each variable, that is each variable symbol like P or Q, is either true or false. Now, the truth value of an arbitrary formula is decided from the truth values of its atomic variables using something called a truth table. However, a truth table is something that you're familiar with. It's not always the best method of deciding the truth value of a formula. I'm going to talk about this a little bit more later on. Writing a truth value is an exhausting job, and sometimes it's just unnecessary for many purposes. And there are no effective algorithms to do truth values. To write truth tables. So we're going to be a little bit more official in this course and define the notion of truth value of a formula properly. This is how it should be defined, not just using a table, but using a function or set of functions that actually gives a mathematical meaning to the table. So those functions are states. What's a state? The state is a function that takes atomic formulas and gives either true or false. So your inputs are atomic formulas, and the output or the range of the function is a set with two elements, true or false. So a function, we usually denote it by V for state, not S for state, V because of the value. So this really, this V stands for value. It's a function that takes atomic formulas in its domain. So the domain is the set of all atomic formulas, and the codomain is the set with two elements, true or false. But that's not any function like this would be called a state. There is one more condition, such that V of top, the value of top, is always T. And value of bottom is always false. So a state is a function that takes an atomic formula and it gives true or false to it, but with the condition that to the top, it always assigns T, and to bottom, it always assigns F or false. Now, we want to extend these functions to not work on all atomic formulas, but on all formulas. So we want to extend the notion of the domain of these functions from atomic formulas to all formulas. And we're going to extend it recursively. We're going to give a recursive definition for V. This is a recursion on the complexity of formulas. So this is the concept that we just talked about. We defined the notion of a state for atomic formulas. Now we're going to define the notion of states, which is a function for all formulas recursively. So how do we do this? By the way, states are denoted by V, V prime. So we're going to stick to this letter V and use superscript, subscripts, and so on. I don't think we're going to need any other letter. V is good enough. So how do we define V of negation of A? So assuming that V of A is defined, right? It's a recursive definition. We defined functions called states for atomic formulas, and now assume they're defined for the formula A. We want to define it for a formula negation of A. V of negation of A is defined as follows. V of negation of A is true if V of A is false, and V of negation of A is false if V of A is true. So if we know what V of A is, if V of A is defined for for the formula A, then this is how you define the value of negation of A in this state. Note that there are infinitely many states, right? These are functions on a set of all atomic formulas, and there are infinitely many atomic formulas, therefore there are infinitely many states. But we are just defining the notion recursively. Now that we have done this, we want to assume we have A and B are defined, and defined we have A and B. We have A or B. We have A implies B. We have A is equivalent to B. This is how you define. We have A and B here. It's definition by cases, right? We're defining it. We're assuming we have A and B. They're both defined. If we have A and we have B are both true, the value of A and B, if you plug in, again, I want to make an emphasis, this is a function. This is when you plug in A and B inside this function V, you get T, true. If we have A is true and we have B is false, the value of A and B in this state is going to be false. If we have A is false, we have B is true, the value of A and B in this state is going to be false. And again, if both of them are false in this state, we have A and B is false. See, we assumed we have A and B are defined. That is the function is already defined for formulas A and B. And we defined the function for A and B. It's a recursive definition of such a function. You can define this similarly for A or B. And this, how we define this is according to our understanding of and or, right? A value of A and B is only true if both values of A and B are true. Otherwise, it's false. And this is exactly how we defined it. Now, the value of A or B is true if at least one of A or B are true. That means if V of A and V of B are both true, then the V of A or B is true. If V of A is true and V of B is false, V of A or B is true. If V of A is false, V of B is true, still true. If they're both false, then V of A or B is false. Again, something that we expect to happen for this junction. It's only false if both A and B are false. A implies B. If we have A and we have B are true, we have A implies B is true. We have A implies B is going to be false only if we have A is true, we have B is false. Right? If your hypothesis or premise is true, but your conclusion is false, that would be the only case that A implies B is going to be false. And that's exactly how we are defining it recursively, right? Now, if we have A is true, we have B is false, this is going to be false. If we have A and B, we have A is false, we have B is true, is true. If we have A and B are both false, then the value of A implies B is true. Finally, the value of A is equivalent to B is going to be true if and only if the values of A and B are the same. So if V of A is equal to V of B, V of A is equivalent to B is true. Otherwise, it is false. Right? This is exactly what these four conditions are saying. Any questions? So what did we do? We defined these functions called states first by defining them on atomic formulas. meaning the domains of the functions were atomic formulas, and the codomains were the set with two elements, true or false. And then recursively, we extended the definition for all formulas. Now we can plug in any formula in any state, and it's defined. Now, in order to calculate exactly for a given formula, let's say P and negation of Q implies R or P, we want to find the value of this. This value is defined recursively from the values of P, V of P, V of Q, and V of R. So if you give me these values, then I can recursively find the value of this. And that recursive operation is just what truth table does, right? It keeps track of this evolution of the truth value through the complexity of the formula. So in terms of truth table, so let's also relate this to a truth table that we are more familiar with. Now, so what's a truth table then? A truth table is exactly this function. The states are a table that we basically keep track of all the possible states. So a truth table is going to be a table like this, where here we're going to, in the first row, we're going to list all the possible subformulas of the formula. So rows are going to correspond to subformulas. Now the columns are going to correspond to particular subformulas. So this would be a subformula, this would be another subformula, this would be another subformula, and so on. But the rows are going to correspond to possible states. So each row is going to represent a possibility for a particular state. So let's start here. I'm going to go through this quickly, and then come back here. If you have a formula A, this is not a complete truth table, by the way, because A could be a complicated formula, but let's for a second assume A was an atomic formula, a variable or a constant. If it was a constant, then you don't need a truth table, because constant cannot, if for example you have top, then you cannot have F. So let's say A was a variable. Then the negation of A is another formula if A is true. So this is a state. This corresponds to all the states. So this corresponds to all states such that V of A is true. And this line corresponds, or this row, the second row corresponds to all the states where the value of A is false. Now, if V of A is true, we have negation of A is false. If V of A is false, we have negation of A is true. So now this row here, let me, for example, go for this third line. Now we are writing the truth table for AND. So this third row corresponds to all states such that V of A is false and V of B is true, and so on. So the first row is going to correspond to all the states that V of both A and B are true. So if V of A is true, V of B is true, then V of A and B is true, and so on. So this is what truth table does. Its columns are the subformulas of your formula, and each row corresponds to certain states. And all together, all these four possibilities, they exhaust all possible states. So when you put all your rows together, all rows would correspond to all possible states. So that means you just consider all states. So it keeps track of everything inside a table. And similarly for or and implication and by implications, the truth tables are here. These are some things that you're familiar with, but we're going to define a few concepts, and you see that sometimes truth table is good, sometimes it's basically useless. When your formula is complicated, there are a lot. It's actually better to work with states as functions to prove something rather than using a truth table, which could be very, very lengthy. All right, our next definition is the definition of substring. I'm going to first define it, a subformula. First, I'm going to define it directly, then I'm going to define it recursively. So in order to define the notion of subformula, first I'll define the notion of the substring. So B is a substring of the string A, means that for some strings C and D, A is equal to C, B, D. This is the concatenation of these three. So for example, if I have a string of formulas like this, it's not even going to be a formula. I'm just going to write a string. This is a string in the alphabet of Boolean logic. Now, if I take this to be B, this is a substring. Why is it a substring? According to definition, because there exists another string C and another one D, such that if I concatenate C, B, and D together, I'll get my string A. So here B is a substring of A. Note that C or D could be empty. We usually denote the empty string by lambda. So if B was this entire thing, now what is B? B is the empty string. Still, B is a substring of A. So here, D is going to be lambda, the empty string. Now that we have defined the notion of substring, we can define the notion of subformula. A subformula of a formula A is a substring of A, which is itself a formula. So if I start with a formula let me write something perhaps looking more new. Something like this. Let's call this A. What are exactly subformulas of A? For example, if I take this substring here, it's a substring. B is a substring of A, but is it a subformula? It is not, right? Because B itself, B is negation of P with this left bracket. It's not a formula. It's not a well-formed formula. Although it is a substring, it is not a subformula. But if I took, for example, B to be negation of P, then it is a substring, but it's also a formula itself. Note that I didn't write those outer brackets around negation, but assume they're there. So negation of P is a subformula of this formula A. Now, this is one way to define the notion of subformula, but we could also define it recursively. And this would be a better definition, at least. It depends on really the purpose of your definition. But this is a definition that you could actually code it, and a computer will find subformulas. So it's a systematic way of defining this notion of subformulas. How do we do this? First, we are going to define the subformulas of atomic formulas. That's how you define something recursively, right? First, you define the concept of subformula for atomic formulas. That is, in this case, we are going to define the set of all subformulas of an atomic formula. An atomic formula is a variable like P or Q, or it's a constant like top or bottom. What are the subformulas of an atomic formula? An atomic formula has only one subformula, and that's itself. Note that the string itself, maybe I shouldn't have erased that. Instead, I erased this. Any string is a substring of itself. And now, if your string happens to be a formula, then that means any formula is a subformula of itself. Now, if your formula happens to be atomic, then it has only one subformula. If it's P, then its subformula is only P. There are no other subformulas. The subformulas of top, but there's only one, top itself. For bottom, it's the same. So any atomic a subformula of an atomic formula is itself. And that's it. There are no other ones. Now that we defined, we understand subformulas of atomic formulas, assume we know the subformulas of A. Let's define the subformulas of negation of A. What are the subformulas of negation of A? Well, the subformulas of negation of A, so assume this is my A. This was, let me write that here. If A is P and negation of P or bottom, then the negation of A is the negation of P or negation of P or bottom. Actually, negation has higher priority, so if I wanted to do that, I need these brackets. This is negation of A, not the one that I wrote first. You need the brackets. Now, what are the subformulas of negation of A? Note that any subformula of A, let's say P is a subformula of A. Negation of P is a subformula of A. And so on. There's only one extra subformula. Any subformula of A is going to be a subformula of negation of A, but there's one more, and that's the entire negation of A. So let me write this. The subformulas, let me give you an example. Subformulas of negation of P or P implies top this time. What are the subformulas? P is a subformula. What else? Negation of P is a subformula. Top is a subformula. Negation of P or P is a subformula. There's one more subformula left, and that's the entire formula itself. Now, what are the subformulas of the negation of the above formula? Again, any substring that it's a formula itself, it's a subformula. So P, negation of P, sorry, I wrote bottom here, I meant top. There's no bottom in the, here, top, negation of P or P, negation of P or P implies top, and finally the entire formula. I also forgot this brackets. I meant to have two brackets here. So negation of P or P implies top, the entire formula. So what are the subformulas of negation of A? That is all the subformulas of A plus the negation of A itself. Now I assume you know the subformulas of B and C. You have defined them. And here circle is a connective that is either, so I don't want to write this 4 times. So let's circle denote either one of these connectives. So it's a symbol that belongs to one of these 4. And so let's say if it was AND, then what are the subformulas of B and C? Any subformula of B is a subformula of B and C. Any subformula of C is also a subformula of B and C. There's one more, and that's the entire thing itself, B and C. And that's how you define it. And these two definitions actually coincide. They're the same. All right, we are out of time. I'm going to stop here to think about this a little bit more. And have a nice weekend. Well, I don't think I'm going to see you until next week. So have a nice weekend. Have a nice day. See you next time.